As Albert Einstein emphasized in the special theory of relativity proposed in 1905, it sets the maximum pace of causal interactions in ordinary space. That is, an effect cannot transpire in less time than it would take for its cause, journeying at light speed, to reach the place where it happens. For example, you couldn't somehow rattle a moon rock remotely faster than a laser could reach it. In general, no transaction involving matter or energy might exceed the speed of light traveling through a vacuum. Moreover, anything with mass, meaning most elementary particles, must travel slower than light. It would take an infinite amount of energy to accelerate a massive subluminal particle up to light speed, which would clearly be impossible. Though well established by means of numerous experiments, the speed limit for the transfer of matter and information is unintuitive. Why should natural transactions have absolute bounds? In races, records are meant to be broken. With spaceflight, we aspire to travel faster and faster. Banks reward loyal customers by raising their credit limits, offering them a sense of financial freedom, whether real or illusory. No one likes to be fenced in. We like to breach any frontier. Yet, like a sleepy town hoping to slow the pace of tourists rushing through, special relativity imposes a universal cosmic speed limit. And why that particular value? Did an early dynamic process cement the speed of light cap, or was it always unwavering? Could there conceivably be other versions of the universe, or universes parallel to ours, where the speed of light is very different? Could there be any enclaves of reality where it is unlimited? Special relativity assumes that the vacuum speed of light is fixed and finite, but doesn't fully explain why. In 2011, a startling headline in the prestigious journal Nature, "Particles Break Light Speed Limit," describing a new research claim, jolted the scientific community. Physicists could scarcely believe the news. Given the overwhelming support for the basic precepts of special relativity, including the speed of light barrier, many were dubious. The type of particle in question was the extremely lightweight neutrino. First hypothesized by the brilliant quantum physicist Wolfgang Pauli, the neutrino is nearly, but probably not quite, massless and electrically neutral. Consequently, it rarely interacts with other particles, doing so almost exclusively by means of what is called the weak interaction, a type of interaction involved in certain kinds of radioactive decay. Neutrinos are exceedingly common. Nuclear reactions in the Sun generate them constantly. They travel rapidly through space and flood Earth every single moment. However, because they interact so rarely, the vast majority simply pass through. Thus, precisely measuring their speeds is challenging. We couldn't simply bounce them, for instance, as we would photons, particles of light, off lunar reflectors and time their return. The method used by the OPERA, Oscillation Project with Emulsion Tracking Apparatus, team of physicists, was to record the time of flight of neutrinos produced at the LHC, Large Hadron Collider, and detected at the Gran Sasso Laboratory, a special facility housed in a highway tunnel to protect from the interference of other particles. The group reported that the neutrinos completed the journey in about 60 nanoseconds, billionths of a second, less time than the speed of light would predict. While they published their results only after allegedly ruling out a wide range of possibilities for experimental error, alas, other competing teams couldn't reproduce their superluminal value. Eventually, the supposed finding turned out to be purely a glitch in the timing system. Alas, the so-called faster-than-light neutrinos were merely a mirage. The opera experiment notwithstanding, we cannot assume that any scientific hypothesis will last forever. As sacrosanct as Einsteinian special relativity seems today, scientists might someday find a way to circumvent the speed of light barrier. Indeed, general theory of relativity, introduced by Einstein a decade after special relativity, contained an important